Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be trying to better understand the factor theorem. And to be able to do that, we need to build up ideas so that we may sort of get our understanding in a suitable way. A good place to start is this proposition. Let's look at the statement of the proposition. It says if we've got two polynomials, f of x and p of x, and of course these two are taken to be non-zero polynomials, right? Then what it's saying is we can divide f of x by p of x and get something called q of x and r of x, which is obviously the quotient and the remainder respectively, and write it in this form such that the quotient and the remainder are actually unique, right? So that's quite an important thing. And the other thing is that the degree of the remainder, or in other words, the order of the remainder, has to be less than the order or the degree of the polynomial that we were dividing by. Okay? So we won't quite see a proof of this because it's a bit too hard for the purposes of A-level, but since the idea or the actual statement of the proposition is used very, very frequently in A-level from as early as the first year, where you sort of start dividing polynomials and so on and so forth, then this is certainly worth knowing, right? So I'm going to say proof is omitted. However, we are going to consider a special case. So let's think about it. What we actually want to do as a special case is take our f of x to be a general polynomial, to say an x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2 and all the way to a1 x to the 1 plus a naught. And of course, we may write x to the naught, but really we don't need to do that because x to the naught is just 1. Right? So once we've written this down, we've got to say that our an better not be 0, because if it's 0, then the polynomial we've got is not really of order n, right? And we don't want to be starting with polynomials that are sort of a different order than what we might think it is. And the other thing we want to say is where all these numbers, where ai are basically real numbers, for I being from 0 all the way to n. So that's our specific polynomial that we're considering. And then the other polynomial we want to be dividing by is actually something which is a linear polynomial, and a very nice linear polynomial. We actually would just, in this case, actually do the division. So we would start with an x to the n plus an minus 1 x to the n minus 1 all the way to a1 x to the 1 plus a naught. And then we'll continue with the division by writing the thing we're dividing by here, and we'll say, okay, what do I need in this first lot, so that when I actually do a subtraction, I end up with nothing in this column essentially, right? So looking at this, we know that we've got to multiply by a suffix n and x to the power n minus 1, right? So here I can write a n x to the n, because obviously the x times by the x to the n minus 1 would multiply to give me x to the n, and then the a to the n will just come along for the ride. And the second term here is going to be c times by an x to the n minus 1, but obviously there's a negative, so I've got to keep track of that. C a n x to the n minus 1, right? So at this stage, we basically do a subtraction. So we do that, and then we say, once we do the subtraction, we get 0 x to the n's. That's precisely why we picked this thing in the first place. And then the other thing we get is we get a to the n minus 1 plus c a to the n. And then obviously all of this is describing the number of x to the n minus 1 terms, right? And then the rest of what I had still needs to be divided. Okay, so here, so obviously the division has a long way to go yet. I've only just begun, but the interesting thing to keep in mind is look, we started with a polynomial of order n, and only after having done the first step, we end up with a polynomial of order n minus 1. Okay, so I'm going to write that down. So I'm going to say each step of the division reduces the order or maybe I want to say degree, of intermediary polynomials by 1. Now, this is a very, very significant thing to say because if I'm going to do this division and I'm going to start with something which is a degree n or order n, where n is some whole positive number, and each step I do, it's going to reduce the degree by 1, as I've sort of said here, then ultimately, as we keep doing successive steps, intermediary polynomials that are going to turn up are going to have lower and lower and lower degrees. Ultimately, when we end up with a case where we end up with a polynomial of degree 0, essentially. So let's write that down. So another way of saying the exact same thing that I've just said is basically because of the statement in red, uh, when the division stops, the remainder in this case will have to have degree 0, right? So in other words, the remainder is going to be constant, and that's quite reassuring because if we actually think about this, our degree of x minus c is actually 1, and our degree of say a constant number is actually 0, and we see that we have this, right? Which is exactly the same thing as this condition here. Okay, I've just got the inequality written the other way around. My p of x is actually here, and my r of x is actually here. Okay, so I should add that we've obviously not finished this long division, but the point is we don't really need to, right? The key point we wanted to get out is actually here in green. Okay, in fact, I'll write it here. So the special case actually tells us that when we divide a polynomial f of x by a linear function, say x minus c, the remainder is a constant. Okay, we can now move on and look at the factor theorem. The factor theorem, what does it actually say? Well, it says if we've got a polynomial function f of x, which is non-zero, and c just happens to be some number, then the factor theorem actually says two things. The first thing it says is if you put c into f and you happen to get 0, then x minus c is guaranteed to be a factor of f of x. Okay? So statement 2 says if x minus c is a factor of f of x, then f of c is actually 0. Okay? So I should perhaps point out the slight subtle structure that's happening here. Statement 1 is saying something like a implies b, and statement 2 is actually saying something like b implies a. So what these two statements together actually mean is A is exactly the same thing as B. So in other words, if f of c equals 0, then x minus c a factor, and if x minus c a factor, then f of c equals 0. That's the complete statement of the factor theorem. Let's make a bit more room and jump straight into the proof. Proof. So we're going to start with a proof of statement 1. So we're going to say assume f of c equals 0 for some c. We want to show that x minus c divides f of x. Divides f of x, right? So, well, let's just do the division. So let's do this division directly. We know that by proposition 1 there's going to be a q of x and there's actually going to be an r of x, right? Such that we can write something like this down. However, we can actually go further and we can say since x minus c is linear, then by our special case, which is what we talked about, we know that the remainder is a constant, so we can say f of x over x minus c equals q of x plus, let's just call the constant r, capital R, x minus c, where r is a constant. Of course, that's our remainder, right? But what can we now say? Well, we can multiply the entire equation here by x minus c, and we end up with this. We end up with f of x is equal to q of x times by x minus c plus r, But now we can substitute x equals c. So when we sub x equals c in, we get f of c is equal to q of c, c minus c plus r. But of course, c minus c is going to be 0. And because that's 0, that tells us that whatever qc is, it really doesn't matter. Something times by 0 is just going to give me 0. So the whole thing actually tells me that r equals f of c. However, what do we know about r? Well, if r is f of c, we know that f of c is actually 0, right? Because that's our assumption. We picked precisely a c, which we know when we put into f we get 0. So since that's the case, we can actually say this actually is 0. But now, if r is 0, that means there is no remainder. So we say, therefore, there is no remainder, right? Another way of saying that is we can basically come back here, or even here, and we can put r equals 0, right? So once I do that, what I actually end up with is f of x over x minus c is equal to q of x, right? And of course, there's going to be a plus 0 over x minus c, but that's precisely the point, that because the numerator is 0, we actually have nothing there at all. So we can just get rid of that. So, of course, here, now we say that f of x equals q of x minus c, which means x minus c perfectly divides f of x, right? Because we can write it as a product of two things. So we've been able to show that provided there exists a real number c such that when you put it into f to get f of c, and if that happens to be 0, then actually the x minus c is a factor of f of x, right? So let me make a bit more room and we can try part 2 of this theorem. I've written down the second part of the theorem, and let's prove this. So now we want to be starting with the statement on the right, which is assume that x minus c is a factor of f of x, and we want to show that we're gonna be able to show that f of c equals 0. So since x minus c is a factor of f of x, then what we can say is we can say f of x divided by x minus c is actually going to give me something like this, where because it's a factor, I know that the r of x is actually going to be 0. In other words, what we actually have is we have f of x over x minus c is actually perfectly equal to q of x, right? Another way of writing that, of course, is just f of x is just q of x times by x minus c. So that's really just a direct consequence of the very, very blatant statement that we've actually got here. Now let's substitute x equals c into this statement here, right? Into the statement star. So when we substitute x equals c, we get f of c is equal to q of c times by c take away c. And again, just like last time, c take away c is going to give me 0. And of course, it doesn't really matter what q gives me when it's evaluated at c. Whatever it is, times by 0 is going to give me 0. So once it gives me 0, what I've actually already been able to show is that f of c better be 0. So in this case, we've been able to go from saying that x minus c is a factor of f of x to being able to show if that's the case, then f of c has to be 0, right? So this completes the proof of the theorem. Before bringing this video to an end, let's take a look at the remainder theorem, which is a more generalized version of the factor theorem. And the statement says, let f of x be a polynomial, then f of c, where c is some real number, is the remainder obtained when we divide f of x by x minus c. So let's quickly take a look at a proof of this. So, so we say let c be a real number, and we say divide f of x by x minus c. Okay, then by the sort of thing we saw in proposition 1, we know that f of x over x minus c is going to give us some quotient, plus it's going to give us some remainder, and of course we've got x minus c. But now we can say by special case that we considered, r of x equals r, where r is a real constant. is a real constant. So in other words, this thing here, f of x over x minus c, is actually the same thing as q of x plus r over x minus c, right? And this again makes sort of good sense because the degree of that is less than the degree of that, right? And that's precisely what proposition 1 told us. So at that stage, we multiply through. This is the exact same argument as the one we gave last time. We multiply through. So we say f of x is equal to q of x times by x minus c plus r, where of course r is the remainder. So then we can say substitute x equals c. And when we substitute x equals c, we get f of c is equal to q of c, c minus c plus r. And it's the exact same argument as we've seen already. C minus c gives us 0, and of course anything times by 0 is going to give us 0. So what that actually tells us is, perhaps I should do it in black, what that tells us is actually f of c is equal to r, right? But r is our remainder. So that is r equals f of c is the remainder obtained when f of x is divided by x minus c. With that, I'd like to bring this video to an end. We hope you found this useful. Do let us know in the comments section as to what you would like to see more videos on. Thank you for watching, and we'll see you in the next video.